Average velocity is easy to compute. Remember, it's as simple as v average is delta x over delta t, but it's not particularly useful. It depends on the start and the end of the interval you pick, and essentially acts as if your velocity is constant, but you know that your velocity can vary. Imagine that you're driving home today after class and a friend calls you. You don't pick up. You should never answer the phone calls while you're driving, but your passenger does answer, and the friend asks, "How fast are you going?" You wouldn't say, "Hold on, count to 10, and measure the distance so as to get to slope." You'd look at the speedometer, which shows that your speed at that instant. Moreover, you know the speedometer will show a different number a little while later as you try to pass a slow-moving truck. This is the concept behind instantaneous velocity, the velocity of an object at a particular instant in time, not over some average. The average velocity is the constant velocity that gets you between 2 points at the end of an interval. And we'll come back and talk a little bit more about the difference in a bit. But, kind of spoiler alert, nature cares a lot more about your instantaneous velocity than your average velocity. Average velocity is very dependent on human beings and therefore doesn't enter into the equations. How might you estimate the instantaneous velocity? Well, you might see how far the object travels in 1 second and compute the average velocity that way. But you do better to measure after only half a second, and it'd be even better to measure after only, say, 1/10,000th of a second. In fact, you'd like to measure as small a time interval as possible. Mathematically, we say that the instantaneous velocity is the limit of the average velocity as we consider infinitesimal time intervals. In other words, as the delta t becomes very, very tiny. And we see that in notation here, the instantaneous velocity v is the limit as the delta t's become 0, as they approach 0 of this ratio. Of course, when delta t is 0, delta x is going to be 0 as well, and you get 0 over 0, which in math classes is a warning sign, but in physics just means something's gone wrong on our derivation. And not even that, but just that the quantity has to be set by some physical parameter rather than mathematical parameter. Notice that the v here is no longer given any kind of subscript. It's no longer v sub average, and we don't write v sub inst. V without any kind of qualifier is assumed to be the instantaneous velocity because it is overwhelmingly the velocity that will be useful for physical equations. Also, as a side note, this mathematical process of taking a limit is the basis of differential calculus, which is a whole different math class. And we will do the bit of calculus that we need in here conceptually, but there's lots and lots to learn about where it comes from and how to use it in a more pragmatic sense, how to formally manipulate things to get their derivatives. But for us right now, all we really care about is the concept, which is that the quantity of the velocity is a ratio of two infinitesimals, and it's a limiting process. Graphically, the instantaneous velocity is the slope of the line tangent to the xt curve. The tangent line pierces the graph at the moment of interest, but the graph does not cross the tangent line there. Put it a different way, a line is tangent to a curve if it divides the plane into two regions and the curve does not cross regions at that point. It can actually cross regions somewhere else, but just if we want this to be a tangent line at that point, then at that location the curve should not cross the tangent line. In the graph we have shown here, let's go highlight. In this graph, the line tangent to the graph at t equals 1 is drawn. All right, so we have to specify what moment we mean. So we go to t equals 1, go up to the graph, and we need a line that touches the curve but does not cross through it. Then we would compute the instantaneous velocity by taking any 2 points on the line and find the slope between them. And it's important to realize that we would say on the line, not on the curve itself, because we're not using the curve anymore. We've drawn our tangent, and so we might say between t equals 0 and t equals 2 on the line. Notice how badly they're not fitting the curve at that point. And then we would just compute it, and we'd say the average velocity there turns out to be, it looks like, just about 0.9 meters per second. A really important special case. When the xt graph has a maximum, the tangent line will be horizontal. That means its slope is 0. But remember, the slope is the velocity on a position time graph. So where the xt graph has a maximum, the object is at rest or not moving, has a velocity of 0. The same will apply where the curve has a minimum. Either of these together are called the extremums. But do keep in mind that this connection, that max or min is at rest, holds only when it's a position graph. If you're graphing something else like a velocity, then it won't be that much. On a velocity graph, it's a little easier. Where the velocity graph crosses the t-axis, we know the velocity has to be 0 because that's what a graph means. All right, a student is shown the velocity time graphs of two objects and is asked to decide which object is moving faster. So here's our two objects. And the student responds, B is faster because it has the steeper slope. What, if anything, is wrong with the student's statement? What they've missed here is it's a velocity time graph. So the slope is not the velocity. The value is the velocity. And at any given time that we pick, if we go up and we look at the curves, we see that B, for any of them, is less than A. If we do over here, we say take this time, we have this is less than that. And if we go over here, we have this is less than that. B is always less than A as shown, so B is always slower than A in this, at least in the window shown here. The position time graph shown represents the motion of two children, Ariel and Byron, who are moving along a narrow, straight hallway. Part A. Do either children ever change direction? If so, at what time or times does this happen? Well, in both cases, the slope of the tangent line is always positive. For Ariel, the position graph is a line, so its slope is constant. So velocity never changes. It's always positive. For Byron, it's a little trickier, but not too much. That if we draw a tangent line, we see that no matter where we draw that tangent line, it's always got a positive slope. And so Byron never goes into a negative direction, so Byron never changes direction. Part B. Are the two children ever at the same position along the hallway? If so, at what time? Well, equality, being at the same position means having the same coordinate, that x sub Ariel equals x sub Byron. Equality in algebra is the same as intersection on a graph, so where the two position graphs intersect is when they have the same position. That happens at 2 seconds, and it happens at 9 seconds. And part C, do the two children ever have the same speed? If so, at what time or times does this happen? Here we want to build this backwards. Having the same speed would mean having the same velocity or having velocities in opposite directions that have the same magnitude. Here they're both heading positive, so I don't have to worry about that. So we really do mean having the same velocity. And the velocity is the slope of the line tangent. For Ariel, the velocity is constant because the Ariel has a line, and lines are the curves of constant slope. So all we're really worried about is Byron. And so the question is there ever a time when Byron's curve has a tangent which is parallel to Ariel's? That occurs at 6 seconds. Right, we can see that occurs when, right here, the purple line here is a line parallel to Ariel's. So it's a line that has the same slope and therefore has the same velocity. And what I ended up doing is moving that around on Google Slides until it was tangent to Byron's curve. And we'll say the moment where that is the tangent is the place where the velocities are the same, which looks to be about 6 seconds.